In this class, we are going to study galvanic cell. A galvanic cell is an electrochemical cell which converts the chemical energy of a spontaneous chemical reaction into electrical energy. In electrochemistry, we study about galvanic cells, fuel cells, the batteries and electrolysis too. So, in electrochemistry, we study the conversion of electrical energy into chemical energy to carry out the non-spontaneous chemical reactions in electrolysis. So, in electrolysis, we study the conversion of electrical energy to chemical energy, and in galvanic cells, we study the conversion of chemical energy to electrical energy. So, chemical energy of a spontaneous chemical reaction is converted to electrical energy by galvanic cell. Conversion of chemical energy into electrical energy. In a galvanic cell, two half cells are there. So, galvanic cell is made up of two half cells or redox couples. One is named oxidation half cell and second one is reduction half cell, or oxidation half cell is also termed as anode half cell and reduction half cell as cathode half cell. Now, in each half cell, one metal rod is dipped into its own salt solution. So, in each half cell, one metal rod is present dipped into its own salt solution. Like for example, here zinc rod dipped into zinc sulphate solution, and copper rod dipped into copper sulphate solution. Internally, these two half cells are connected by a U-tube named as salt bridge. So, internally half cells are connected by salt bridge, and externally they are connected to a voltmeter by a metallic wire. This one is named as salt bridge. In salt bridge, inert electrolyte like for example potassium chloride, potassium nitrate are present in agar-agar paste. So, in salt bridge is an electrolytic, inert electrolytic solution. Here inert electrolytes like potassium nitrate, potassium chloride are present in agar-agar. This is an example of galvanic cell. If we take the zinc and copper rod dipped into their salt solutions, this cell is called Daniell cell, which is an example of galvanic cell. Here zinc rod dipped into zinc sulphate solution and copper rod dipped into copper sulphate solution. Usually when a metallic rod is present into its own salt solution, a metallic rod present into its own salt solution have two tendencies. The metal ions reach to the electrode, reach to the rod, and they get reduced and deposit here, and the metal from the rod ionize means oxidize into solution. These two processes occur simultaneously. Metallic rod gets oxidized and the metal ion get reduced. Now, according to the tendency of the metal which is having more metallic character gets oxidized here, like zinc here gets oxidized and copper gets reduced here. So, in a Daniell cell, zinc loses the electron, zinc rod loses the electron, forming zinc 2 plus ions. Oxidation occurs, and because of the electron it gets negative potential, and this electrode is termed as anode, having negative potential. Zinc rod loses the electron, forming zinc 2 plus ions, and at cathode, in anode half shell, zinc rod changes into zinc 2 plus, and in copper half shell, copper rod dipped into copper sulphate solution, the copper ions present in the solution, they reduce and change into copper metal, and here they get deposited, copper metal gets deposited here on the rod. So, here copper 2 plus from ion gains electrons, doing reduction, changing into copper metal, which gets deposited at the electrode. So, cathode gets positive charge due to copper ions accumulation here, and only anode gets negative charge due to electrons. A potential difference is maintained between two half shells, cathode having positive potential and anode having negative potential. Therefore, a current flows from cathode to anode due to the flow of electrons flow from anode to cathode, from zinc sulphate solution to copper sulphate solution, and the current flows in opposite direction of the electrons flow, that is from cathode to anode. We can measure the potential difference between the cathode and anode in the voltmeter, which is given as E cell. So, the potential difference or EMF of the cell can be given as E cell, which is equal to E cathode minus E anode, equal to E cathode minus E anode, as the current flows from cathode to anode from high potential to low potential. The salt bridge maintains the flow of electrons from anode to cathode, and it also provides the oppositely charged ions to maintain the electrical neutrality of half shell solutions. As the concentration of zinc ion increases here in anode half shell solution, the salt bridge provides oppositely charged ions to maintain the electrical neutrality here, means negatively charged ions, and as the copper 2 plus ion concentration decreases here in cathode half shell solution, the salt bridge provides the positively charged ions to maintain the neutrality of the solution. So, salt bridge plays two roles here, maintaining the flow of electrons from anode to cathode, and second thing, it maintains the flow of electron and it gives the electrical neutrality, it balances the neutrality of half shell solutions by providing the oppositely charged ions. And now the electrode potential of the cell can be measured by taking the potential difference from cathode and anode. E cell will be equal to E cathode minus E anode. For Daniell cell, which we have taken just now, Daniell cell zinc copper assembly, E cell can be given as E cathode means copper 2 plus 2 copper minus E anode means zinc 2 plus 2 zinc. According to IUPAC, we can take only reduction potential, not the oxidation ones. We can take only the reduction potentials for each half cell. For cathode half cell, copper 2 plus reducing to copper, and for anode half cell, zinc 2 plus reducing to zinc. So, only reduction potentials can be taken. Now, if we take the concentration of the solution, if concentration of half cell solutions is unity, it means 1 molar and temperature 298 Kelvin, then the electrode potential will be termed standard electrode potential. At 1 molar concentration of each half cell solution and 298 Kelvin temperature, the cell potential is termed as standard electrode potential given by E naught value. So, we can say E naught cell, which is equal to E naught cathode, for example here copper 2 plus 2 copper minus E naught anode. From E cell means from the voltmeter giving the potential difference of the cell, we can determine the potential difference between the cathode and the anode half cell, but we can't determine, we can't measure the individual half cell potential. Like we can get the E naught cell standard electrode potential of the cell, but we can't measure the electrode potential of half cells. An individual half cell electrode potential cannot be measured from a galvanic cell. So, to measure the individual electrode potential of a half cell, a standard hydrogen electrode was proposed. A standard hydrogen electrode SHE, a standard hydrogen electrode, according to convention of IUPAC, its electrode potential of standard hydrogen electrode is taken 0.00 volt. So, standard hydrogen electrode helps to measure the electrode potential of any individual half cell. What is a standard hydrogen electrode? A standard hydrogen electrode given by SHE in standard hydrogen electrode, hydrogen gas at 1 atmosphere is passed, hydrogen gas at 1 atmosphere is passed through 1 molar hydrochloric acid solution. It is passed to 1 molar HCl solution at 298 Kelvin. Means taking the standard conditions, the 1 molar acid solution and 1 atmosphere hydrogen gas is passed through it, and this inverted tube contains